Young double slit. Okay, so what we're going to do is we're going to take the idea of light acting as a wave, and we're going to do something really, really interesting with it. So this is called the Young's double slit. What we're going to do is we're going to imagine the following. Imagine that we have a barrier, okay? And in that barrier, we cut 2 slits, okay? They're very just small slits. Oh, a double slit. Look at that. So brilliant in naming. Now what we're also going to have is some distance away, and we're just going to call this distance down here. We're going to call it L. This is just a viewing screen. So it's just like a board or something that the light can hit, and when the light hits it, you'll see it. Okay, so it's just a viewing screen. It's like where the room ends, so to speak. Now we're also going to see here, and just defining some things, that the distance between the center of these 2 slits, we're going to call that D, little d. Okay? And to finish the setup here, we'll do the following. We're just going to build some dotted lines going perfectly across to hit our viewing screen like this. Try to do it better than I am here. And that is what we are going to have for the double slit setup. Now, what is actually happening in the Young's double slit? Well, what we begin to do is we shine some light onto these double slits. So it comes in from the left, and as light's acting as a wave, we're going to bring the light in. Here it comes, and then bam, it hits the double slit here. Now, an important feature of this is our light has to be monochromatic. Okay, so it is, our light has it's monochromatic. And it is coherent. So our light, not only does it have the same wavelength throughout it, but it's in the same phase of that wavelength all throughout the light beam. And we'll talk exactly what we mean about coherency and phase once we kind of show this setup. Okay. So when this light hits, the light could enter, into this region through the top slit or the bottom slit. And let's have it enter through both of them. And let's have it strike the dead center between the slits here. Okay? If the light does this, let's look at how far this light is going to have to travel. If we go from the center of the slits and we arrive at this point in the middle, we should readily see that this light travels the same distance. Okay, from the top slit to this point out here on the viewing, from the bottom slit to that point out there, the light is traveling the exact same distance. Okay, there is no change in the amount of distance the light has traveled. On the flip side, and we're still going to pretend that this light is green, but I'm going to draw it in a different color just so that we can see what is going on here. Flip side, let's look at way up here on the viewing screen. If we go from the bottom slit up to this viewing point, or we go from the top slit up to the viewing point, it's pretty readily apparent that these lines have different lengths to them. The pink line is longer than the blue line. That's going to be critically important for what we're going to do, okay? But we know that the pink line is longer than the blue line. Well, how much longer is the pink line than the blue line? Well, we can find out, but to do so, we need to make a quick little assumption. We're going to assume that this viewing aperture is far enough away, so the viewing screen here is far enough away that the angle between our horizontal dotted lines going across and the pink, and the horizontal dotted line going across in the blue, we're going to assume that these are both the same angle, and we're going to assume that they are pretty small angles, okay? So both thetas here are the same angle, and we're going to say that they are small angles, okay? Or they're small enough. Now, I guess they technically don't have to be small angles, but to kind of show this proof and how we can do this, it works easiest for that. But pretty much what we're really saying is these angles have to be the same. Okay, they have to be the same here, even though when you look at this and how we've drawn it, they clearly don't look to be the same. But if this viewing aperture is much farther away, then they start getting close to be the same, and it will work for the wavelengths we're talking about with light. So if those angles are the same, what can we do with this? Well, if we go from our top slit and we draw a line so that that line becomes normal to the pink line down here, that line is normal, so it's 90 degrees. We see that we've generated a triangle. And that triangle goes from here, with the hypotenuse being side D. We see we have a base here, and then we have this, and I'm going to put it in blue right here, okay? If we go for the blue line from the upper slit to the pink dot on the viewing screen, or we go from down here on that bottom right corner of the triangle where the blue circle is to the pink viewing dot, those triangles are now the same. This and this are now the same sides of the triangle, okay? That's just a nice isosceles triangle there. The extra distance is given to us just from here to here. And what's really great about this is, technically speaking, since these angles are the same, this angle on the inside is the same angle as well. So we can now figure out what this extra distance is. If knowing that this D is our hypotenuse and this would be like our opposite side, we can quickly state that our opposite side here is just going to be equal to D sine theta. And that opposite side, we're going to call it some extra distance. So we're going to call it some delta L. Okay? So that delta L there, or so that extra little bit of distance, is just equal to the slit separation D multiplied by the sine of theta. Okay? And that right there, that is a very important idea. This D sine theta is some extra distance that the light has to travel. So let's talk about now why we care about this delta L, this extra distance that the bottom light had to travel versus the top light. So let's just go back for a second and think about sine and cosine on the unit circle. So if you unwind sine and cosine on the unit circle, you would get some sort of graph that would look like this, right? You know, like that's a sine graph. Oh, that's it's not bad, but it's not great. Let's do that. Ooh, that's much better. So we know this is like pi. We know this is 2 pi. This is 90 degrees, aka pi over 2. And this is 270 degrees, aka 3 pi over 2. And then, you know, here's 0. And then once we hit this point, it cycles and it does it again, right? So when our light is coherent, what this means is that every single bit of light that comes in is moving up and down along this wave pattern at the exact same way, okay? And they are all going to be at a maximum at pi over 2 at the same time, okay? They're all moving together. Well, if one ray of light has to travel a little bit further, then some really bad things can happen. For instance, if I had a ray of light that had to travel just a little bit further, then what could occur is that this ray of light may, and let's pan this to the left, this ray of light may have gone up and down, and then if it continues on its sine wave, it would go like this. Oops, missed that one. And I'd see something like this occur. Well, this is bad. Well, it's not bad, it's a feature. What we see here from the red wave up top and the blue wave in the bottom is that these waves are out of phase with one another. They're not both going up at the same time. They're not both going down at the same time. In fact, they are so perfectly out of phase that they are going to not only interfere with each other, but they're going to completely destructively interfere with one another. If I were to add these waves up, the red wave would go up here, and let's say it had a maximum value of 1, an intensity of 1. Well, if I add that to the blue wave when it's at its minimum of -1, well, 1 plus -1 gives us nothing. And if we do this all throughout the waveform, we see that we're always going to have opposite values everywhere. This is 0 and 0 at this perfect point right here. So when these waves used to be in phase, if one of them had to travel just a little bit further, I don't know, some amount like a delta L, if that delta L is the perfect amount, then it will turn these waves out of phase, and the light will interfere with itself, and it will get rid of its own intensity. The light will essentially interfere with itself in such a way that you won't see any light, which is a really, really weird idea. But that's what happens. And we know that waves can interfere both constructively for higher amplitudes or peaks, or destructively, like we see here, which lowers things down. So if this delta L is just perfect, we can actually take light and make darkness out of it. And that is what could be happening up here at this pink point. If this delta L that we found is perfect, we can actually get a dark point out of it. So how could we say this in general? Well, in general, what we can say is that that delta L, that d sine of theta, okay, that's that extra distance. What would that have to be equal to in order for darkness to be generated, for us to have a completely a completely destructive interference? Well, if the light was all coherent to enter, but this extra distance was here, this extra distance would have to be half of the wavelength of light. So this distance right here, that is the wavelength over 2. That's half the wavelength. Because remember, you can take a wavelength from any peak to peak, trough to trough, whatever, but it's a repetition. So if from here to here, that full 2 pi, if that's the wavelength, then half of it is the wavelength over 2. So if you're completely out of phase, you're going to be off by a wavelength over 2. Now, what is somewhat nice about this is that this means that if you're off by an entire wavelength, like if I go way back here, and I'm going to draw it into my diagram a little bit, but if I go way back here and do this, well, if I'm off by an entire wavelength, I've come back into coherency, and I'm good again. So if I'm off by an entire wavelength, I'm going to see the light. If I'm off by wavelengths over 2, I'm going to have destructive interference. So what we can say is this. If this delta L, this d sine theta, if it is an integer amount of wavelengths, so if m equals 1, 2, 3, 4, you get the idea of how to count, then what we will see is we will see a bright spot, okay? Or a fringe, as we call them. So we'll see a bright spot or a bright fringe that exist. If, however, though, this d sine theta equals a half integer value of the wavelength, then we're going to get a dark. And I guess what I should really do up here, excuse me on this, I'm a boo-boo. These m's can actually start from 0 in this case. So it'll be 0, 1, 2, 3, 4. For the dark spots, d sine theta will equal m plus 1/2 multiplied by the wavelength, with m equaling 0, 1, 2, 3, 4. You get the idea of how to count, okay? And the reason being is that when we look at an actual graph of this, if here is our viewing screen and here is the center, we call this point here m equals 0. That is the central node. it is the maxima of the Young's double slit. When we go up to the higher order fringes, this would be like m equals +1, and on the other side, it'll be m equals -1. It's symmetric, so it doesn't really matter if the m's positive or negative, but they are just the same. So if we were taking a look at this, what we'd actually see is that on what's going on here for these m values, we would see this entire spacing here would be a wavelength. So we would see a dark spot if this is at some point lambda, and this is at some point minus lambda, and this is at some point lambda over 2, and this is at some point minus lambda over 2. Here would be dark, and here would be dark. So we would see some sort of large central peak, and then these have to be bright points again at lambda and minus lambda because we're once again coherent. So our light comes back up, and then we kind of see a pattern like this. Okay, so that's the pattern we're going to see out of this, with our central peak being the maximum, the brightest spot at m equals 0. And then as we tail down, we kind of see these decrease as we go out fringe to fringe. Okay, and in the next video, what we're going to do is we're actually going to look at a simulation of this so we can see this a little bit better. But the equations we are going to need for a Young's double slit are right here. And it's important to understand that this light is interfering with itself, and that interference is causing bright and dark fringes that we see.